previous video, we successfully created the data file, and now we are ready to run our first iteration. Let's go back to our example of cobalt to iron aluminum. We have 60 key points in the reducible wedge of a Brilliant zone, and RSPt uses key point-wise parallelization. So to run the code efficiently, we would use 20, 30, or 60 cores, for example. So let me run on 60 cores and see what happens. In my case, I have two nodes with 64 cores, but I cannot use 64 of them because then 4 cores will be idle. They won't have any key points to calculate, and this is not allowed. Okay, so it looks like the first iteration was done. We can look at the produced out file. It has a lot of information, so let me go quickly through. This is a table of nearest neighbors. So this parameter 2s over d tells you how close the muffin tin spheres are. 0.95 is a good number, so it means that the spheres are almost touching, but not quite, and it's a good choice. So between cobalt and iron, we have 2s over d of 0.95. But aluminum atom is a little smaller, so it has 0.9. Okay, it's still acceptable, but maybe we want to increase the muffin tin radius of aluminum. And we come to an important table here with energy parameters. Here you have to watch out for the stars in the second column. Here, this is basically a number of nodes calculated within muffin tin, and it's compared with a nominal number of nodes which the basis function is supposed to have. So we go through and we see that it looks all fine. Great. So we continue. This is the parameter which you have to watch out for to make sure that you have a sufficient Fourier grid. So this argument should be at least 6. And if it's less, then you have to increase the FFT mesh in the Fourier grid file. I also look in this parameter, electrons added. It shows you how many times the code didn't manage to diagonalize the Hamiltonian. And if this number is bigger than 10 to minus 4 or 5, I would start to get worried. And maybe the solution here would be to modify a little bit the basis set, so changing slightly the kinetic energy tails, or adjust the key point mesh. It can be that you're just hitting some unfortunate key point. One of these two usually helps. And this is a very important table with calculated charges within muffin tin. So we start with cobalt, type equal to 1, S states energy set 1 and 2. So these are 4 S states of cobalt, and these are 3 S states of cobalt. So they belong to energy set 2, and indeed there are 2 electrons in 3 S states. They are completely filled because they are lying at very low energies of about 5 Rydberg below Fermi level. Then we have P states. Again, semicolor P states are here. Excellent. There are 6 of them. And finally we have the D states. And they are in the first energy set. We can see that there are 2.73 electrons in spin down channel and 4 electrons in spin up channel. So we can expect to have a magnetic moment of about 1.3 Bohr magneton. Here the information about iron and aluminum. We can just scroll down. This is also important to check. Here, these are the charge densities calculated at the muffin tin, and these are from interstitial. at the muffin boundary they have to coincide, and if they are not, so if these two numbers are different by more than 10 to minus 3, most likely what you have to do is to modify the Fourier grid, or maybe you have to adjust your muffin radii. These are the calculated magnetic moments after the first iteration. Indeed, on cobalt we have about 1.3 Bohr magneton, and that's exactly what we would expect from the occupations which we saw above. Iron has a magnetic moment of roughly 2.6. There is some small induced momentum on aluminum. There is something left in the interstitial, and the total moment is 5.16 Bohr magneton. This is unconverged value, just what we got after the first iteration. So after that we can just go to the bottom of this file and check the Fsq value. So Fsq tells us how much the density and the potential is converged. And by running RSPt many times, this number should go down. And ideally we would like to reach numbers such as 10 to minus 11 or 12. So let's just run one more self-consistent iteration. Okay, let us have a look at the out file again. And now this is the out file of the second iteration. And if we look at this table, we suddenly get stars in the second column. And you see, so this corresponds to energy set 2, where we are supposed to have 3s and 3p states. It means that for any reason, we didn't get the correct number of nodes. So this is a bit dangerous. It can easily lead to appearance of ghost bands, and that would be really bad. So let's see, we got this error for cobalt. And also for iron. And this is unfortunate, but we didn't get it after the first iteration and only after the second one. So you see, if we were to run this calculation, we would discover this error a little too late. So to be on the safe side, what I usually do, I modify the element file of such tricky elements as transition metals. So to make sure that 3s and 3p states have allocated where they are supposed to be, the easiest thing is to put their linearization energies in the center of gravity of these states. And this is done by using the flag -1. So we use -1 flag for 3s up, 3s down, as well as 3p up and 3p down states. Now this flag 20 and 21, actually what it does is that it ensures that this orbital is orthogonal with respect to this one, and this one is orthogonal to this one. So this is a good thing to have. We can keep it as it is, but maybe we don't even need to orthogonalize it, as long as 3p states are lying deep down in energy. But I usually leave these two flags intact. Okay, we go to element file of cobalt and also put these flags to -1. We have to regenerate the data file. Yes, these lines were modified. And now we can run the code once again. And now if we go through this table, we can see that there are no stars. which means that we are safe and calculation should be fine. Once again, we go through the most important parameters, such as electrons added. Okay, still very low. We check arguments. It's still 6, which is good. And finally, we check magnetic moments. We started to change. Okay, now we get a magnetic moment close to 5 Bohr magneton. And what about Fsq? It's still quite large. Okay, it means we have to run a couple of more iterations. So we can converge it, then 10 to minus 12. Now we have to wait. And looks like it's done. So we can look in the hist file, and it contains the summary of the last iteration. We reached the Fsq value of 10 to minus 13, which is excellent. This is the total magnetic moment in Bohr magneton, and this is the total energy in Rydberg. So now we can have a look in more detail what happened. Again, we check the same things, we check that there are no stars. It looks good. Fixing the semicores was the only thing which we had to do. The arguments are again at least 6, which is also good. Electrons added is small. Well, projected averages looks like everything makes sense. The semicore states are completely filled. For the D states we have some magnetic moment. At the boundary the correspondence looks good. And these are the magnetic moments. 1.2 Bohr magneton on cobalt, 2.73 on iron, and small induced moment on aluminum, with a total of 4.94 Bohr magneton. It looks like the calculation is indeed converged. So that's it for today, and enjoy RSPt.